Hi everyone, thank you. So I'm a researcher at Microsoft, and we are trying to build a large-scale fault-tolerant quantum computer. And my research is about quantum error correction. I'm working mostly on two topics. First, what are we going to do with the first generation of fault-tolerant quantum computer? Can we optimize error correction, decoders? And in the long term, can we use better codes? Can we build a fault-tolerant quantum computer with cheaper error correction? And quantum LDPC codes are one of these schemes that could reduce the cost of error correction. There was many breakthrough in the past few years, and I'm going to talk about how to make quantum LDPC code practical. So even though it's long-term, it fits in the topic of this conference, and I think there is still a big gap between the theory of quantum LDPC code and how to make them work, how to build them. And it's a joint work with Michael Beverland and Maxime Tremblay, who was our intern. And all the plots I'm going to show are based on Maxime's work, who did a great job at simulating all these circuits and all these codes. So first, why do we care about quantum LDPC codes? I'm going to look at the cost of error correction. And by the cost, I mean number of qubits used divided by number of qubits stored. So how many extra qubits do we need to store a given number of qubits? And if you don't use error correction, the minimum is 1. All your qubits are useful. If you think about the first codes introduced, short code or the 5-qubit code, have an overhead of 5 and 9. And the surface code, with distance 25, even without counting ancilla qubits, is an overhead of a few hundred. And now what about LDPC codes? For classical LDPC code, like in the flash memory of your laptop, it's below 1.1. There is a giant gap between those two things, between what we are using in the first generation of fault-tolerant quantum computer and what we have in our current devices, in our current classical devices. I'm not claiming that we are going to reach this point with quantum computing, with quantum information. Quantum is much more noisy, but we can try to get closer, at least. And the question we care about is, can we implement these codes? What do we need to implement these codes? There is a lot of theory work, but before this work, there was not even a circuit. We could not implement this code. We didn't have a circuit. We could not simulate them because we didn't have a circuit. So your typical quantum computer looks like that. And the implementation question is, how do we map our typical quantum LDPC code in this quantum computer? And the bad news is that your typical LDPC code looks like that. It looks like a complex expander graph. And you can imagine it's not trivial to map it in 2D. And our main results, the main results I'm going to discuss today are, what can we do first with 2D local gates? So if we have gates like local CNOTs in our square grid of qubits, then the bad news is that either we need a large depth circuit or we need many ancilla qubits, and we lose the advantage of LDPC codes. And we observe a poor performance. So 2D does not seem to work well. And to go beyond 2D, we looked at using long-range connections. So we propose a design with some long-range CNOTs. And in this case, we designed a layout based on a few layers of long-range gates. And we observe that quantum LDPC code can outperform surface codes. So it could work in principle. And this is our second result. So first, I'm going to review surface codes, the circuit used for surface code, and then we're going to try to adapt it to general LDPC codes. So the surface code, it's a grid of d by d qubits. So here you have 9 qubits in a square grid. And you're going to run error correction by implementing a circuit on each placket. The circuit looks like this circuit on the left. It prepares an ancilla on each of the placket. And then you implement a sequence of 4 CNOTs or control Z gates. And you measure. So it you can implement all these circuits in parallel on all the plaquettes. And it looks like that. At the end, you measure, you have your outcome, and you can use this outcome to run error correction. And how does it work in this circuit? On the left side, you see what's happening when there is a Z error on one of the qubits. First, it's propagating through the circuit. It's still there on your qubit at the end of the circuit. But it's also propagating through the CNOT, and it's going to flip the measurement outcome. You can detect it, and you will be able to correct it. OK. And why do we use these codes? Why do we like surface codes? This is a 25 by 25 surface code, and it drops the error rate from 10 to the minus 3 to 10 to the minus 12. And the advantage is that, first, it has a high threshold. You only need to be below 1% noise for all of your gates and all your qubits. So it tolerates a lot of noise. And it can be implemented in 2D. We can imagine it's going to be difficult with those expander graphs. But the main issue is that it costs thousands of qubits per logical qubit. And here it's 1,200. That's why we moved to quantum LDPC codes. So I'm going to give you a brief history of quantum LDPC code, very biased and only in one slide. So I'm not going to cite many of the great results in the field. My apologies. But first, they were introduced as a generalization of classical LDPC code by McKay, Mitchison, and McFadden. And in this context, it was mostly communication. You have noise in a communication channel. You send data using quantum LDPC code. And what they observe is that they can work, but they also observe that the minimum distance is very poor. Yes, they are stuck with a log distance. So you cannot correct many faults. The first satisfying family of quantum LDPC code are those hypergraph product codes. I'm going to review the construction later by Tillich and Zemmour. And I'm saying satisfying and not good, because good means something different. By satisfying, I mean that they correct a polynomial number of faults. Where we can correct square root of n, of order square root of n faults, which is better than a log. But it's still not the end of the story. And they moved to the quantum computing setting with Gottesman, who showed that if we use these codes for quantum computing, we can, in principle, have constant overhead, constant space overhead, with a fault-tolerant quantum computer, which is very exciting. And we know that they have a good performance, but only for a simplified noise model, for phenomenological noise, which means no circuit. We would like to know how they behave with realistic noise, with a circuit. And finally, recently, we learned that we can build good quantum LDPC code, so we can have codes with parameters that are just as good as classical LDPC code, with a linear minimum distance, not a square root of n only. So this is very exciting, but we still don't have a circuit. We still don't know how they perform with realistic noise. And this is the first thing we're going to do. We're going to design circuits. And we're going to design them based on the Tanner graph. It's a way to represent the code. So it's a bipartite graph, a graph with two types of nodes. The circles are going to represent bits or qubits, and the squares are going to represent checks or stabilizer generators, constraints on the code. So a bit string belongs to the code if it satisfies the constraints defined by the square. And each constraint is a parity constraint, mod 2. So the sum of these three bits, x1, x2, and x4, must be 0. And it's LDPC if all these bit and check have bounded degree. Now we have a sparse graph. It defines the code. And we can do the same thing in the quantum setting. So first, on the left, it's a classical Hamming code. And we can detect a flip by looking at the constraints that must be satisfied. When we flip one of the bits, it's going to flip the constraint that is connected. So we're going to see a non-trivial parity, which indicates that there was a fault, and we can correct with that. In the quantum setting, we do the same thing with two types of checks. one for X errors, one for Z errors. So when there is a Z error, it's detected with the blue checks, with the top checks. And with the X error, we use the bottom checks. And we can do the same thing with two classical codes. There is some constraint, but we are going to get it for free in the family of code we consider. And you are familiar with the surface code. So it looks like that in the language of Tanner graphs. You have your square grid of qubits, of d by d qubits, 3 by 3 or 5 by 5 qubits. And you have checks alternating between X and Z checks on the plaquettes. Okay, now the family of codes we are using, it's hypergraph product codes. And they are built from the product of two graphs, of two Tanner graphs. One horizontal, one vertical. And we are first going to place qubits. We place a qubit on the product of a square on a square, a circle and a circle, sorry. And the product of two squares give us another type of qubits. So we have two groups of qubits. And we're going to define those two checks, Z checks and X checks, by looking at the product of circle square. And we connect them horizontally and vertically according to the two input graphs. And we are going to place a Z on the incident qubits. So like that, we can define a Z check. And we can do the same thing with X check by taking the other product, square by circle. And by looking at the incident qubits, we define a check. As you can see, they overlap in two positions. So the corresponding check commutes. It's properly defining a code. And it's the family of hypergraph product codes. Why do we care about these codes? I told you with LDPC codes, we can get many logical qubits. We can get more logical qubits than with surface code. It's cheaper. And in the case of surface code, for instance, if we have n data qubits, we have also about n ancilla qubits, and we encode one logical qubit. If we look at hypergraph product codes, we have a similar number of data qubits and ancilla qubits, but we have a constant number of logical qubits per physical qubit. So instead of one, we have a growing number of logical qubits. It's going to be the main advantage of these codes. Now let's start by laying them out in 2D. So the first thing we are going to do is that we're going to obtain a bound, a lower bound on the best circuit we can get. Why? Because if I design a circuit and I tell you they have a poor performance with this circuit, you're just going to tell me that I did a poor job at designing this circuit. So I want to convince you that we design a circuit that is optimal in some sense. So we obtain a lower bound. The lower bound is telling you that the depth of the circuit in 2D is lower bounded by some constant times the number of data qubits of your code divided by square root of the total number of qubits you are using, including ancilla qubits. And this bound can apply to two settings. So in the case of surface code, your depth is 6, right? You have 4 C nodes, 1 preparation, 1 measurement. And if you apply this bound, in the case where you want a constant depth, you need this bound to be constant, then you need Q to be of the order of n squared. So the total number of qubits must be of the order of n squared. You need many ancilla qubits. And it's bad news. We want a small overhead. We don't want to use many ancilla qubits. The alternative is to say we want a small number of ancilla qubits. Let's say the number of ancilla qubits is linear in the number of data qubits. It's proportional with n. But then this lower bound tells us that the depth is at least the square root of n. So in both regimes, we are in trouble. Either we have a large depth or we need many qubits. And we design circuits that achieve this bound. I'm going to show you one of them. And I'm going to show you the simulation result for the other. So let's build a circuit that achieves this bound using as many ancilla qubits as we want, but so n squared, but using a constant depth. So first I'm going to do assuming fully connected qubit, and then I'm going to lay it out in 2D. So the circuit for the measurement of a check, it's the same circuit as the surface code. We measure the C naught along the edges of the Tanner graph, one at a time, and then we measure our check. Now let's do that simultaneously for all the checks of our code. Here we have 3 checks. And we're going to start by building an edge coloration. When we build an edge coloration, we're going to... Okay. So we're going to start by preparing a plus state for each of our check, our ancilla qubits. And then we're going to loop over the colors. And for each color, we're going to apply a C0 along the edges with the same color. These edges do not overlap. We can do it in parallel. So in a depth which is given by the degree of this graph, or the number of colors, we can implement the measurement of all the checks. Once we are done in constant depth. We can measure all these checks. Now can we do it in 2D? So to move to 2D, we are going to map these 3 C0s implemented along red edges here, green edges, in this 2D grid. It's a grid of size n by n, so it's going to give us our extra n square qubits that we need. We cannot do it with fewer. And we're going to map on top, we're going to put our data qubits, our code qubits, and in the bottom, the ancilla qubits that measure the check. And now I'm going to put a label on top that corresponds to the connection I want to establish. So the first check must be connected to this data qubit. On the graph on the left, it's what I see. And I want also a connection between the second check and the data qubit number 6. To do that, I'm going to create path from the top to the bottom, and we're going to do it with a sorting network. We want to, so I'm adding the missing digits, and I'm going to swap them to put them in a sorted order. So I sort even pairs and then odd pairs, and I keep going. And at the end, after n swapping, I get a fully ordered sequence. 1 is in front of 1, 2 is in front of 2. And that means I can build a path along those numbers to connect the bottom ancilla qubit number 1 with the data qubit indexed by number 1. Now we just need to implement a C0 along those paths. I could do it in 3 steps, but I cannot do it simultaneously because those paths are crossing. So here we are going to use a little gadget to implement those crossings. And the gadget we use, I will call it a switch. That's why it's a switch-based circuit. It's based on entanglement. We are basically going to create a virtual edge that we can use once, and once it's used, it's destroyed. Entanglement is destroyed. We need to re-prepare it. How do we do that? We prepare a bell pair. We can do it locally. So we prepare 2 bell pairs horizontally on these 4 qubits. And then we swap 2 of them. We can do it locally again. What we get is 2 crossing bell pairs like that. And those crossing bell pairs will be implemented along all the crossing. We can do that in constant depth. Once we have them, we can establish a connection from the bottom to the top in parallel along the 3 paths, even though they are crossing. We added virtual edges. And we can use a long-range C0 to implement our long-range gates. By doing that, we get a constant depth circuit, and we use n square ancilla qubits, but we know that we cannot do with fewer. So it's a fairly good circuit. What do we get in practice? So Maxime simulated these circuits, and the bad news is that with fully connected qubits, we use a small number of ancilla, we have a constant depth, and we have a pretty good performance. The threshold is of the order of 10 to minus 3, a bit below 10 to minus 3. Sorry, a bit below 10 to minus 2. But when we look at the 2D case with a large depth, then the performance degrades. And this is the cost of locality. It's about 3 orders of magnitude. It doesn't work. The performance is very poor because we have a large depth circuit. So this is a simulation for the large depth circuit with a small number of ancilla. In the other case, we have too many ancilla qubits, so we're also in trouble. So we need a new idea. Let's try with long-range connection. So the first thing to try is to say, let's put all of our qubits on a circle and connect them the way we want. This is a graph with 100 qubits, 100 nodes, and degree 8. And I'm not an experimentalist, but I will not want to implement that in a lab. It's very messy, and what we assume is that because of all these crossings, when we try to implement CNOTs along those edges, if there is noise during the CNOT, it's going to propagate through the CNOT, but it's also going to propagate when those CNOTs are crossing. And it's going to give us extra noise that propagate quickly to the whole graph. So we want to avoid those crossings, and that's going to be our motivation. We believe they introduce correlated errors, so we want a small number of crossings, and we want a short depth circuit, because large depth does not work. And our idea is to split the Tanner graph into different planar parts. So for instance, for this one, we can look at the first and the third check. I moved the third check on top so that they don't cross. There is no crossing edges, so we can implement CNOTs in parallel in a planar way here. And with the second check, we have also a planar subgraph. So here we have 2 layers. We have degree 4 and 2 layers. And we can generalize this strategy for a general graph. If we have a CSS code, and if we have a degree delta, then we end up with a standard extraction circuit with delta over 2 planar layers, and with depths proportional with delta. So we have bounded depths, a small number of layers, and planarity within the layers. It looks like that. Here we have 4 layers. This corresponds to the case of our simulation, where we have a code with 4 layers. And you see that within each layer, you have only planar edges. You have no crossing. But if you look at it from the top, if you do not use this layered layout, then you have many crossings, and we're worried it's going to lead to correlated errors. And what do we get numerically? If we assume that the noise, we have some noise rate for each gate at the circuit level, we get a threshold which is 0.3% instead of 0.7% for surface code. So it's lower, but it's actually surprisingly high. It's not that bad. And the main advantage is that we are using 49 qubits for each logical qubit, independently of the distance. When the size of the system grows, we never reach more than 49. We stay at 49 qubits per logical qubit. We have a constant overhead, including ancilla qubits. And now we counted the number of qubits, the total number of qubits we need for different regimes that correspond to different applications. You can think of 10 to minus 12 as Shor's algorithm, or maybe chemistry at 10 to minus 15, or your logical error rate. And we start with a physical error rate at 10 to minus 4, below the threshold of our LDPC codes. And then we estimate that we can achieve the same logical error rate as surface code for a quantum memory with 15x fewer qubits. So we have a significant saving in terms of number of qubits compared to surface codes. And it's with a simulation at the circuit level. Okay, so I'm going to conclude here. First, our main result is that we have general bound for 2D local circuit, and these bounds are tight. We can build optimal circuits that reach these bounds, and we can show that numerically that LDPC code can outperform surface code, even with a similar noise model. That's the good news, but it's not the end of the story. There is a lot of work to do, both on the theory side and on the experimental side. So first, on the theory side, we can use better LDPC codes. We used hypergraph product codes that have a distance which is square root of n, but we have new codes now. We have better codes, so we can look at some of these codes to even improve further this 15x. And we need to build explicit construction from these families. The second thing is that we didn't look at logical operations. There is a lot of work in that direction. I think it's a very exciting question. We need a way to implement logical operations. We considered only a fault-tolerant memory, but at some point we need to compute on top of that. And another thing is that we use a suboptimal decoder. There is still no fully satisfying decoder for quantum LDPC code, but there is a lot of work in that direction. And that's one of the questions I like particularly. And in some sense, it's a good news that there is so many open questions with quantum LDPC code. That means that this 15x, maybe it's optimistic, but there is a lot of potential improvement for the next few years that could increase even further this number. And that could motivate people to look at experimental implementations. Because there we need a lot. We need long-range connections. I'm not an expert of experimental results, but I don't think there is any fully satisfying long-range connections. And in addition to that, we need many of them. We need many of them within insulated layers and with little crosstalk. So it's a big requirement, but hopefully we're going to make progress in that direction, and all the encouraging theoretical result is going to help to motivate us to look into that. Thank you.
Yeah, we have time for a few questions. 1, 2.
Thank you for the talk. Thank you so much for the talk. It was really interesting. The insulated layers, what kind of conditions do you need in order to separate these layers but still be able to, like, what are the operations you need between the layers, and how much separation, say, error can you tolerate for just this layer separation specifically?
I have only a very vague picture in my mind, and it's on purpose. I don't want to send you in the wrong direction. I don't know. Here, what we have in mind is that in these vertical columns, like here, each square corresponds to a qubit. So we must be able to implement a long-range CNOT in each layer with the same qubit. So the same qubit must be able to connect to a qubit in that direction, and in the layer below to another qubit that is connected. There is many ways to implement that. Maybe we can think it is really the same qubit, and we have some wiring going through different physical layers. Maybe we can use 4 qubits and encode them to represent one small logical qubit. There is many ways. I don't know what is the best one. And I think this kind of thing is very open as far as I understand. So. Thank you.
I had a question on the way that you structure the syndrome extraction. And that have you looked at interleaved scheduling of? I mean, you're looking only at CSS codes, right? Like, but have you looked at interleaving the CNOTs for the Pauli X and then the Pauli Z, and do the same type of sorting tricks work in that regime?
So we did not, and in some sense, it's another good news that we don't know how to do it, interleaved XZ measurements, and that could even improve further the performance. Our circuit is not claimed to be fault tolerant as well, so we can also improve there and boost a little the minimum distance. Because it has constant depth, it's enough to make sure that we only divide the minimum distance by a constant, but this constant can still be large. So there is a lot of potential improvements there. Yeah, that's right.
Yeah. Okay. Hi, thanks, Nicolas. Can you tell me if you hook errors is what I want to ask about. So one of the beautiful things about the surface code is that you can use a single ancilla and you never have an issue that a single error will propagate through the circuit and become a weight 2 error that aligns with the logical. So here you're only using one ancilla, so you're not using any flag gadgets. So is it also the case that because hypergraph product codes are kind of related to the surface code, that hooks aren't a problem, or do you encounter hooks?
So the circuit we design is similar to the surface code in some sense. If we apply it to the product of 2 repetition code, we recover the initial circuit with the same orientation. But I don't believe it's fault tolerant. I don't believe that we avoid hook errors. We just don't care. It was enough to show good results. I don't mean we don't care. I mean it was enough, and we would like to improve that in the future. It's a potential
I
improvement.
guess if there were bad hooks, it would make me wonder what the effective distance was as opposed to the actual distance, and then that might affect how you can extrapolate to 10 to the minus 15 error rates, etc.
Yeah, it seems that they are not too bad, but we didn't even analyze the effective distance.
Okay.
In the previous slide where you had the bell pair crossings, is it required that I should have bell pair crossings over all possible pairs or all possible like 4 points, or is it just where it's crossing?
It's only where it's crossing. We use them only to implement in parallel a connection along those crossing edges. So here we only need 2 of them.
Thank you so much again.
Thank you.